In this video, our goal is to explain four things. The first thing is rate law or rate expression and order of a reaction with respect to a specific reactant. And also we will explain overall order of a reaction. And we cannot explain this without a term called rate constant and its units. We already learned that how to write the relative rate based on the stoichiometric relationship between the reactants and product using the coefficient. That means we were comparing the rate of disappearance of reactants and the rate of appearance of products based on the coefficient in the balanced chemical equation, and we call that one as stoichiometric relationship or relative rate, right? So in this video what we will try to explain is the rate expression or the rate law, which is purely based on the experimental value, and we are going to use only the reactant, not the products. Okay, and we are not going to use the coefficient in the balanced chemical equation. So the rate law expression or the rate expression is nothing but is the relationship between the reaction rate and the concentration of reactants given by a mathematical equation. Let us see an example to explain these two. Consider this equation, general equation, that is AA plus BB, and we can write another one, the reactant if we want to, gives GG plus HH plus another product. If we have another reactant here, we can write that product, right? Okay, so then A, B, G, and H are the coefficients of that balanced chemical equation. So how can we write the relative rate? For this one, we learned before that rate equal negative 1 over A, change in concentration A divided by change in time, that equal negative 1 over B, because we had two reactants we have shown here, change in concentration of B divided by change in time. Whereas in the rate expression, what we are doing is rate equal a constant K, we call that K as rate constant, and reactant concentration A to the power M, and another reactant B, the concentration of B to the power N. So here M stands for order of the reactant A, and N stands for order of the reactant B. And when you add M and N, the sum of the exponents, we call that one as order of the reaction. So what is it telling us about the order is how fast the reaction is going to happen in terms of A. And with respect to B, how fast the reaction is going to happen. So this one we can determine only through experiments. Okay, so the relationship between the rate and the reaction concentration. So this mathematical expression we call rate expression or rate law expression. So for the previous equation, we wrote rate equal K, A to the power M, B to the power N. So if M equals 0, we will say the reaction is 0 order with respect to A. And if M equal 1, we will say that is first order with respect to A. And if it is 2, we will say it is second order with respect to A. Similar to that, if N equals 0, we will say the reaction is 0 order with respect to B. If it is 1, we will say the reaction is first order with respect to B. And if it is 2, we will say the reaction is second order with respect to B. So we will talk about only 0, first and second order reactions with respect to that specific reactant. So what if we write R equal K, concentration A, if there is no number on as an exponent here, by default that is 1, and concentration of B to the power 2. What is that means is with respect to A, the order is 1, and with respect to B, the order is 2. So when you take the sum, that is 1 plus 2, it is 3. So what is the order of the reaction? We will say the overall order is 3. Or we can say it is the reaction is third order overall. More examples. The first one is that is in each case we have to find the order with respect to each reactant and then the overall order of the reaction. So we have the rate expression given. The first one is rate equal K concentration A. We have only one reactant and there is no number as an exponent here. So order with respect to A is 1. And the second example is showing rate equal K, concentration A, concentration B. We have two reactants and on each one we can see only 1 and 1. Even though it is not shown 1, by default it is 1 if nothing is written on top. So order with respect to A, it will be 1. Order with respect to B, it's going to be 1 again. And the overall order is 1 plus 1 equal 2. Third example, rate equal K, concentration A to the power 1, concentration B to the power 2. So we can say order with respect to A is 1 and with respect to B equal 2. So 2 plus 1 will give us the overall order, which is 3. And fourth one, rate equal K, concentration A, concentration B, concentration C to the power 2. So order with respect to A will be 1 and with respect to B it's going to be 1 and with respect to C it's going to be 2. So overall order for the reaction will be 2 plus 1 which equal 4. And now this is what we have to know to find the order with respect to each reactant and the overall reaction order. So from the experimental data, we have to check what is happening with the concentration of the reactant. So in all cases, we can see that when we double what is happening to the rate, so depends on the change in rate, we can actually predict the order. What is that means is, if the initial concentration of the reactant doubles, by doubling that initial concentration, if the rate doubles, we call that one as first order reaction. And if the initial concentration of the reactant doubles and the rate quadruples, we know that the second order reaction with respect to that reactant. And when the initial concentration of the reactant doubles and if there is no change in rate, we call that a zero order reaction with respect to that reactant. So let us explain this one with an example. So this is what we have to remember in order to predict the order with respect to a reactant. To see this example, we have experimental data for the reaction 2A plus B gives 2C, right? So we have three trials here and concentration of A is given here, concentration of B is given here and rate is given here in each three trials. So how can we write the rate expression is rate equal K, concentration A to the power X, that's what we are trying to find, and concentration of B to the power Y. So we have to find the order with respect to A and with respect to B from the experimental data. So what happens here is in trial 1 and 2, the concentration of A is not changing. So we are just trying to double the concentration of B and we will see how the rate changes with respect to B. So we can see that the rate is also doubling. So doubling the concentration of the reactant, doubling the rate means that's going to be first order with respect to B. So we will just replace that Y with the number 1, correct? That is first order. And now let us see trial 2 and 3. What is happening in the case of B is we are not changing B and we are trying to see what will happen when we double concentration of A. And what happened to the rate by doubling the concentration of A is it quadruples. That means with respect to A, it's going to be second order. So we can write the rate expression or the rate law for this reaction based on the experimental data like rate equal K, concentration A to the power 2, concentration B. So overall order is going to be 2 plus 1, 3. Before we are moving on to more examples, let us go ahead and explain how to find the unit of K, the rate constant. So that means the unit of K will be different for zero order, first order and second order. So to make it simple, we can go with the general form of that unit, which is 1 over molarity to the power overall order minus 1 times unit of time. Unit of time can be in seconds, it can be in hours, it can be in minutes, that depends. That depends on the question, it will be given along with the rate. Okay, so let's go ahead and see for each one separate. Okay, for zero order reaction, we can write the unit of K like this. So I will just use the general form, that is 1 over molarity, overall order we said zero order, minus 1. Unit of time for examples I am taking just second. Okay, so that equal 1 over m to the power negative 1 second. So it is in the denominator. Normally we don't write the unit like in the denominator. So what I will do, I am going to take it to the numerator. So m negative 1 will change to m positive 1. So I don't have to show the positive 1. By default it is 1. For the second, it is 1 in the denominator. So when I take it to the numerator, it will be negative 1. So this is for the zero order. So what if it is first order? So if it is first order, we will write 1 over m to the power 1 minus 1 second. So that means 1 divided by m to the power second. So when I take it to the numerator, I can say that it is second inverse. And what if it is second order? If it is second order, 1 over, I'm talking about the overall order, okay? So 2 minus 1 second. That equal 1 over m to the power 2 minus 1 is 1 second. So when I take it to the numerator, it will be m negative 1 second inverse. So what if the overall order of the reaction is third order? So that means 1 over m to the power 3 minus 1 second, that will equal 1 over m square s. When I take it to the numerator, it will be m to the power negative 2 second inverse. So it continue like that. Fourth order you can find like that. Okay. So that's how we can actually write the unit, and from the unit actually we can find out which order reaction is that. If suppose if the R value, the rate value is given, rate equals say for example 0.25, and if it is written just S inverse, we know oh, this is for the first order reaction. So if it is written 0.25 m to the power minus 1 second inverse, we can say that that is second order. If it is just written 0.25 m S inverse, I can say that that's zero order reaction. So we can figure it out what's the order of the reaction by looking at the unit given. Let's see an example here. For example, if it is given rate equal K concentration A concentration B to the power 2. So we know that the overall order for this one is 1 plus 2. So overall order equal 3. So how can we find the unit of K? Here is 1 divided by m to the power 3 minus 1, and the unit of time I'm taking second. It's going to be m negative 2 second inverse. Alright, so sometimes the molarity, as I said in the previous case, molarity can be written as moles per liter, or sometimes you will say mole liter inverse as well. So all are same, but it looks more simple. So I think that is just learn like that, and then whenever it comes like this, you will be able to understand as well, just to make it simple. Now let us see this example. In the reaction A gives B, we have concentration of A, there is only one reactant, and the rate is given. So what happens here is when we move from trial 1 to trial 2, the concentration is doubling. So what happened to the rate? Quadruples. So with respect to A, we can say the rate is 2. And from trial 2 to 3, the concentration of A doubles. What happened to the rate? Rate again quadruples. So we can write the rate expression as rate equal K concentration A to the power 2. So what will be the unit here? Let us try to find the unit of K. Unit of K will be, since it is second order, 1 divided by m 2 minus 1 second. That means 1 divided by m. Yes, so it will be m inverse second inverse.